Welcome, everyone. For today's prep, we're going to start looking at our next major topic, and that is sequences and series. So today we're going to start with sequences. So we're going to look at the definition. We'll see how do we represent a sequence notationally, and in class we'll also see how to do so graphically. And then we're going to see today how to write out the first few terms for a sequence given its formula. All right, so what is the definition? Well, a sequence is a function, and the domain of this function is the set of positive integers. So our function f in this case is going to take a natural number, so a positive integer here, and it's going to give us out a real number. So normally what we're used to is, this is normally the domain over here. And normally what we're used to is functions where this is also the real numbers. So when we graph a function, normally we plot the x-axis. The x-axis represents all real numbers. So normally when we talk about functions, the domain is all real numbers, but for sequences, it's going to be the natural numbers, the positive integers. And a way to think of this, rather than a function, is we can think of a sequence as an infinite list. So a lot of times we'll use these curly brackets, and then we'll list out the first few terms. We'll write out the first few terms, and then we put some dots, and then we have the formula for the general term, a sub n, and then we put more dots to indicate that the sequence continues. And so if we're thinking of this function notation, f of n here represents the nth term of our sequence. So this would be f of 1, this would be f of 2, f of 3. So we're just plugging the integers into this function f, and it's giving us out a list of numbers. And we're really looking to this general term a sub n here as kind of like the formula for this function. All right, so notationally, we're going to be using a few different ways to describe a sequence. So we might write out the first few terms. Again, put these curly brackets around, write out the first few terms, and then put dots to indicate that the sequence just continues. Another time, other ways we'll do it is, again, we'll probably use curly brackets, and then we'll write the formula for that nth general term. Again, we're kind of thinking of this as like the formula for our function. And we start our sequence at n equals 1, and then it goes to infinity. So we're plugging in all the positive integers here, starting with 1 and counting on up. So let's look at an example. Here's an example of a sequence. So we've written it with the curly brackets, so we got our curly brackets here. This one starts at n equals 1, and then we're counting up from there. And this term is the formula for, essentially the formula for our function here. So for this one, the directions say write out the first 4 terms. So let's do that. And we look at this index. We want to think of n a lot of times as kind of like an index here, indexing the terms of our sequence. So it says n equals 1. So that's going to be our first term. Then we'll plug n equals 2 in. Then we'll plug n equals 3 in. And then we'll plug n equals 4 in. And essentially we're going to plug each of these in to our formula, and that's going to give us the next term in our sequence. So let's start with n equals 1. We're going to take n equals 1, plug it into the formula here, and when we do that, we get 3 over, we get 3 times 1. Let's actually write it out. 3 times 1 divided by 2 times 1 minus 1. So all we're doing is we're taking n equals 1, plugging it into the formula here. Now we go to the next one, n equals 2, do the same thing. So let's plug it in. So we get 3 times 2, all over 2 times 2 minus 1. Then we do n equals 3. Again, plug it into our formula here. So we get 3 times 3 all over 2 times 3 minus 1. And for n equals 4, play the same game. We get 3 times 4 all over 2 times 4 minus 1. And then we'll put the dots here to indicate that the sequence just kind of continues. And if we want, we can clean all this up. So for this first one, we end up with 3 over 1. Then for the next one, we end up with 6 over 3, so we end up with 2. And then we end up with 9 over 5 for our next term. And then for our fourth term, we end up with 12 over 7. And we've written out the first 4 terms. So we're really just evaluating a function here. And we're just plugging in, integers in. So that's the main idea here. Is normally when we talk about functions, we plug in real numbers. So we might plug in decimals, we might plug in, things like pi and whatnot. For sequences, though, we're just plugging in just these integers. Now, for this example, we started at n equals 1. We don't always have to start at n equals 1, though. So let's look at example 2. Now, we have this sequence written out. We have -1 raised to the power n times n plus 1. So we have the nth general term here. But for this one, we're starting at n equals 3, and then we're counting up from there. So we can generalize this definition of sequences a little bit. We don't always have to start at n equals 1. So sometimes we'll be starting at n equals 0. Sometimes we might start at n equals 3. So it just depends on the context. N equals 1 and n equals 0 tend to be the most common, though, but not always. All right, so we're going to do the same thing. We're going to write out the first 4 terms, but this time we're going to do it starting with n equals 3. All right, so let's see what we get. Put our curly brackets here. And when we do this, we're going to start at n equals 3, then n equals 4, n equals 5 comes next. And then the fourth term here is going to be for n equals 6. So we're just writing out the first 4 terms. All right, so let's see what we get when we plug n equals 3 in. So we're going to get -1 cubed times 3 plus 1. So that's our n equals 3 term. Then we'll put a comma. And then I'm going to take n equals 4 and just plug it in wherever I see an n. So we get -1 raised to the power 4 times 4 plus 1. Then when we plug 5 in, we get -1 raised to the power 5 times 5 plus 1. And then for n equals 6, we get -1 raised to the power 6 times 6 plus 1. And we're just writing out the first 4 terms, but this continues on. So we'll put some dots, and then we'll close our curly bracket. Let's simplify this, though. So this is going to simplify. So we have this -1 cubed. And we're going to see this -1 raised to a power n quite a bit. So when -1 is raised to an odd power, the result is just going to be -1. And when -1 is raised to an even integer, it's going to be +1. So in this first case, we're going to end up with negative, and then 3 plus 1 is 4. For the next term, this -1 raised to the power 4 is going to be positive, so we're going to end up with just +5. And then we just kind of keep going like this. So -1 cubed is, well, negative. -1 to the 4, positive. -1 to the power 5, back to negative. -1 to the power 6, back to positive. So it just kind of alternates like this. So for our third term, this is just going to be negative, so -6. And then for our last term that we're going to be writing out here, this is going to be positive, so +7. and then it just continues on from here. All right, so this is kind of the idea, is sequences are really just a special type of function, and the numbers that we're plugging into this function are just integers. And a lot of times our sequence is going to start at n equals 1 or n equals 0, but we don't have to. We can start at, say, n equals 3 like we did in this. So where we're going with this is the sequence is our list of terms, and where we're going is eventually we're going to try taking this infinite list here, and we're going to try adding all the terms together, and that's going to form what we call a series. But that's coming up a little bit. But we first want to get a little practice working with these sequences. So we'll do some more in class. So we'll see you then. Bye-bye.